Yeah, in this video, I'm going to talk about the empirical rule. Last video, we talked about chip-shaped inequality, where we had a data set or a population where we only knew the mean and the standard deviation, and we wanted to know how the data is distributed. And we were only able to tell that within one standard deviations, we cannot tell much. Within two standard deviations, we could say there's at least 75% of the measurements, and within three standard deviations, we can say there is 88% of the measurements. Now we have a data set or a population where we know the mean, we know the standard deviation, and we know one other very important piece of information, and that is the data is bell-shaped, which means we did a histogram where we had classes, daily, frequencies, histogram, and it looked like a bell shape. And so we know it's bell-shaped, we have the mean, we have the standard deviation, and we don't have the original data. So what can we say about the distribution of the data? How much of the data falls in and where? And this is what the empirical rule says. It's really a remarkable rule. We're going to tie it into the normal distribution later on when we get to distributions or probability distributions. But for now, let me go over it here in your lecture notes. So if I have a set of measurements which is represented by x1 up to xn, and again this can be a sample or a population, doesn't matter, it works equally well. Then we say approximately 68% of all measurements lie within one standard deviation of the mean, which means in this interval, x bar minus one standard deviation and x bar plus one standard deviation, we have 68% of the measurements. So you can see how the bell-shaped rail plays a significant role here. When we didn't know it's bell-shaped, we couldn't say anything. As far as we didn't know even if it was 5% or 1%. But now with the bell shape, things change. So even if we go to two standard deviations, so I take x bar minus two standard deviations, x bar plus two standard deviations, which means I'm within two standard deviations, then I know approximately 95% of the measurements lie within two standard deviations. And if I go to three standard deviations, that's going to be about almost all, actually more than 99%. It's 99.7%, 0.72% lie in this interval. So, and those numbers, the 68%, the 95%, and the 99.7%, or all, or more than 99%, they don't change. What changes are the intervals depending on the mean and the standard deviation. So if we have same data set we had before, where we have a mean of 75 or a sample mean of 75, a standard deviation of 6, now we know the distribution is bell-shaped. Then if we take the interval x bar minus 75, which is x bar, which is 75 minus one standard deviation gives me 69. Add one standard deviation to 75, I get 81. So this interval will contain 68% of all measurements. If I take x bar 75, subtract two standard deviations, I get 63. If I take x bar, I add two standard deviations, I get 87. And in this interval, I have 95% of all measurements. Same thing, if I subtract three standard deviations, I go to 57. If I add three, I go to 93, and then I get almost all of the measurements, 99.74%. Let me show you this graphically. I have a graph here. So if I look at this graph here, and I go first, let's take this line where the data is, and that's the shape, so it is nicely bell shaped. So that's my mean here. So I go one standard deviation down. So in this case we have mu and sigma for the population measurements. You can use the sample measurements as well. So I have mu minus sigma, and I have mu plus sigma, and I have, in this interval, I have 68% of all measurements. So if I go 2 standard deviations to the left to here, I go 2 standard deviations to the right, I have 95% of all measurements in here, under the curve, of course. If I go 3 standard deviations to the left from up to here, and 3 standard deviations here, so I get almost all of my measurements here. That's about 99.7%. Now, but that's really not all in this, because if you look at this curve, it's a bell curve, it's symmetric. So I know more than just these 3 numbers. So if I go back to the 68%, so that's, I go between this number and this number, but because it's symmetric, I know the 68% is going to be divided equally between this piece here and this piece here. So this piece and this piece. So that's about 34% and 34%. So these are more exact numbers, 34.13. So it's about 34% and 34% here. Well, I know that also in this interval is 95%, but because of symmetry, then this piece should be 47.5%. If I take away the 34.13%, I end up with 13.59%. So about 13.5% here. Again, by symmetry, this piece and this piece are the same. I have 13.5% here, 13.5% here. So if I have again 95% in here, so I have about the 5% here, or a little bit less than 5%, but it's divided equally into these 2 pieces because of the symmetry, how nice this graph is. So that's about 2.5% and 2.5%. So it's, the exact numbers are 2.28% and 2.28% here. So look how remarkable this result is. We only knew 3 things: the mean, the standard deviation, and that the shape is bell shape, is a normal frequency distribution. And what we were able to do here is to divide this into 6 equal classes or intervals, and tell exactly what percentage of measurements fall in each of these intervals. So you see the width of each interval is 1 standard deviation, because we go 1 standard deviation, then another one, then another one here, and we go 1 up, another one, and another one. And so our frequencies, these relative frequencies or probabilities, don't change. What changes from problem to problem are the mean and the standard deviations. So that's how remarkable this result is. I wanted to emphasize that. So for our example, this would be 75. This would be 75 minus 6. This would be 75 plus 6. This would be 75 minus 12. This would be 75 plus 12. This would be 75 minus 3 times 6, 18. This would be 75 plus 3 times 6, or 75 plus 18. Okay. And that's it for this topic. Again, wait for later to find out more about this when we talk about normal distribution. Thank you.